Mathematical induction is a less intuitive way of proving a statement, and it's not even to prove a single statement usually, it's to prove a sequence of statements. So let's let pi be a statement for I equals 1, 2, 3, 4, and so on. And a proof by induction is a proof of all the statements from I equals 1 to infinity of the pi's. So in other words, we want to simultaneously prove that all of these statements are true. And the method for doing that is we first prove that P1 is true. And you might even have to prove a couple more in practice, but to simply state the proof by induction, we'll prove P1, and then for I bigger than or equal to 1, we'll prove that Pi implies Pi plus 1. And so, therefore, since P1 was proved to be true, we know P1 is true, and then using that, since Pi implies Pi plus 1, P1 implies P2, so therefore P2 is true. And since P2 is true, P2 implies P3, and therefore P3 is true. And you can go on and on. So P3 is true, and P3 implies P4, so P4 is true. And they all fall down sort of like dominoes, and it turns out that all of the statements are then proved true. And you can do this if you pick a particular fixed n. So if you fix n, you can trace it back to, well, Pn is true if Pn minus 1 is true, and Pn minus 1 is true if Pn minus 2 is true, and on back until eventually you get to P1, and you can say, well, we proved P1 to be true, and therefore all these statements following are true, and Pn is true. There is a common mistake to assume that if you let I go to infinity, the statement for infinity is true, but that's not the case, because you can't actually trace back all the way from infinity to the original statement. So don't make the mistake of assuming that whatever the claim is, it will be true if you plug in infinity. So we're going to do an example that claims that for I bigger than or equal to 1, the sum from j equals 1 to I of the numbers j is equal to j times j plus 1 over 2. So this is what we want to show for all numbers I bigger than or equal to 1. And so this is the statement P of I. And so we're trying to show an infinite number of statements because we're showing this for I bigger than or equal to 1. And so we're going to do the base case first. And we're going to plug in I equals 1. So on the left side, we get the sum from 1 to 1 of j, which is just the number 1. And on the right side, we get the fraction 1 times 1 plus 1 over 2, which is 1. And therefore, these things are equal. So this sum does equal j times j plus 1 over 2. Now, suppose that that is true for some n bigger than or equal to 1, that the sum does equal the fraction. So the sum from j equals 1 to n of j equals n times n plus 1 over 2 for a fixed number n. We want to show the claim also works for n plus 1 then. And this is our inductive hypothesis. So we're trying to show now that it's going to follow that the sum from j equals 1 to n plus 1 of j is equal to n plus 1 times n plus 2 over 2. And that's just taking the formula that we're trying to show and plugging in n plus 1. So here we're plugging in n plus 1 for I, and here we're plugging in n for I. And if we can show this, then it must be true for all I by induction. So if we sum to n plus 1, that's the same as summing to n, and then adding one more, right? So we're going to break up the sum from j equals 1 to n plus 1 to the sum from j equals 1 to n plus the last term, which is n plus 1. Now, by our inductive hypothesis, we know this sum does equal the fraction. So the sum from j equals 1 to n of j is n times n plus 1 over 2, and the n plus 1 just floats along there on the side. And the last step is just to do algebra by getting a common denominator multiplied by 2 over 2 here, and working it out, you get n plus 1 times n plus 2 over 2, which then does prove the claim.